Thank you, everyone, for coming to the our new episode in this series, Scholarship of Teaching and Learning, Innovative Teaching and Physics Education Research. Today's presenter is Dr. Umesh Silwal from UNC Charlotte. He's going to talk on very important topic, transforming undergraduate physics laboratory courses to foster key 21st century skill sets and competencies. For your information, maybe towards the end of January or February, like there will be another presentation from in this series from a professor at UNC Charlotte from Education Department. So I would like to request Dr. Umesh Silwal to present his material. Thank you.
Thank you, Dr. Rudra Kapli, sir. Can you hear me? Can you hear me?
Yes, please go ahead. Yeah, thank you.
Hello, everyone. Good morning. Namaskar from North Carolina. My name is Umesh Silwal, and I'm working as an undergraduate lab coordinator and associate graduate faculty at UNC Charlotte. And the title of today's talk is Transforming Undergraduate Physics Laboratory Courses to Foster Key 21st Century Skill Sets and Competency. Here is the abstract of this talk. So basically, on this talk, I'll be talking about the traditional lab courses we have in many of the universities and their expected learning outcomes. Then I'll talk a little bit about the effort in evaluating the effectiveness of those lab courses, and we'll talk the American Association of American Physical Society (AAPT) guidelines to develop the lab curriculum and their desired key skill sets for 21st century. Then we'll introduce a couple of methods transferring our lab course. Then I will summarize this talk with the some modification we made in our lab courses and with our future plan. So let's begin with. We all agree that undergraduate lab courses are an essential part of physics curriculum. It involves substantial instructional resources that includes space, time, equipment, and instructors, and it is important to measure the actual educational contribution to ensure those resources are being wisely used. So here is a question: what are lab courses for? Or what is the purpose of having a physics lab course in our curriculum? The answer might be reinforcing lecture content, learning about measurement and uncertainty, practicing communication skill, developing teamwork skill, learning physics as an experimental science. Could you please write down which option you think best for having a lab course in chat box? I'm not seeing the chat box from my screen, but let's spend a couple of seconds. But our traditional lab courses are primarily designed to reinforce the lecture content, but most of our lab courses, they fail to hit all those goals mentioned above. This result is very surprising. Then in most of the university, we have an introductory lab course that is aligned with their introductory lecture classes. So we have two types of lab courses. One is standalone lab course and another is studio class lab course. What does this standalone lab course means? It held in different location and time from lecture course, and students receive separate lab grades or grade that is composite of two parts of the course. And in the studio class, lab and lecture component are completely integrated, and this talk is basically focused on the standalone lab courses. So I have used here the traditional lab a couple of times. And what does this traditional lab means? It is characterized by aiming to reinforce the content of the lecture. Uh, those labs are highly structured. There in the lab manual, it is written what students are supposed to do and how to do them. Or we can say lab manual has everything. It has which equipment to use, how to set up the equipment, how to collect the data, which graph to plot, what parameters or what information they are supposed to extract from the graph, uh, and they will be filling the worksheet at the end of the lab period. So it is like more like filling the blanks or cookbook labs. Uh, and those traditional lab or standard lab, they do not have the opportunity for student in decision making or critical thinking. uh, Natasha Holmes and Carl Women from Stanford University examined the effectiveness of those lab courses, whether they are enhancing content knowledge from lecture or not. uh, Carl Women, he is a Nobel Prize winner from 2001. He won it on the topic uh, Bose-Einstein condensate. Uh, what they did actually here on this analysis is they compared the two group of student who is taking the both lab and lecture courses, and student only taking the lecture courses, and they assume that if lab courses are helping enhancing student content knowledge, students taking both lab courses should have a higher score on the final exam. And here so basically they use a final exam as a proxy to examine the master content mastery of the student. And here they found one problem with this approach. Students decide to take lab courses or not based on their measures and other requirement. For example, students who are major health science, uh, their this physics lab course is compulsory for them, and the population of students who took and didn't take the lab course are different. So it involves the biasness if they directly compare the final exam score with the student who took the both lecture and lab course or just the lecture course. uh, and they come up with the solutions here, uh, as all course materials do not have associate lab activity. So what they did is they normalized the individual student performance on question whose target content was reinforced by a lab activity and that lacked in associate lab activity. They calculated the mean lab benefit. What is it? They basically obtain this mean lab benefit by first calculating each student fractional score on the lab related questions, and they subtract it from fractional score on the non lab related questions. Uh, they calculate the average of those differences of each group of student and then calculated the difference between the group average. So here in this uh, in this equation, if here, let me put interruption here. This first box, it is here LR represent the lab related questions. This NLR is non-lab related questions. Let me explain what exactly they did. Uh, they evaluate the final exam score. They categorize the final exam questions as a lab related questions and non-lab related questions. And if the lab provides the intended benefit, they assume that uh, student who took the lab and lecture course, this should have a larger difference in their lab related and non-lab related uh, uh, questions score. That's what they assume, and they calculate this mean lab benefit. And uh, they compare the student final exam score for the two lab courses and found that the average benefit on lab-related questions for a student who took the lab in both courses was within 0.6% of the score of student who did not, within uncertainty about 2%. So from their analysis, they found that uh, taking the lab course is not beneficial in enforcing student content knowledge from the class. They extended this research for 3 other institutions, uh, for 9 physics lab courses, over 3,000 students, and uh, again the result on this graph. Here the mean lab benefit is indistinguishable with the zero. So the mean lab benefit that at the 3 institutions shows no measurable impact on benefit on student course performance from enrolling in the associated lab course. Furthermore, they carried out similar research for midterm exam scores, assuming any difference could have been washed out by the time of final exam. They restricted the final exam questions only conceptual reasoning, no quantitative calculations, and they produced the same null result for lab benefit again. And they conclude that uh, our traditional lab courses are not helpful in enhancing student content knowledge from the lectures. Our goal for reinforcing the content knowledge seems inadequate. We might argue that lab might have other kind of benefit, and Heather Lewandowski and collaborators from University of Colorado, they examine the student attitude towards lab and experimental physics using the E-class survey. E-class stands for Colorado Learning Attitude and Science Survey for experimental physics, and the results have a negative impact on students taking the lab course on their experimental skills. Then Carl Wayman and his group started thinking about why students do not learn, or why there is no impact on enhancing student knowledge from lecture uh, for the student who take the lab course. What they did was they interviewed 32 students who were doing the undergraduate research experimentation in the summer, who has already taken those traditional lab courses and at least one project lab course before. They simply they simply ask questions like what are they enjoying the most, what are they learning, what has been frustrating for them, and they uh, try to uh, try to analyze those interview questions with these 3 types of lab experience they had before. URE here in this graph represent undergraduate research experimentation. Next one is project lab, and the last one is structured lab or the traditional lab. And this green color here is for no engagement, and we can see that for most of the cognitive tasks for the structured lab there is no engagement, and that's why students are not learning doing the lab. Uh, in their interview, student mentioned remembering the analyzing the data and checking whether it was feasible to finish the lab on time. Uh, Only those things for taking the undergraduate these traditional labs. Then Carl Webben and his group started breaking each lab uh, into the smaller component, and they figured out the interesting fact that decision making is already done for student in advance for each lab courses. Relevant principle and equations are already laid out. Uh, what data to collect and what to collect them, or which button to push to produce the desired result is mentioned in the lab book. Or in summary, lab book mention everything like which equipment to use, how to use the how to set up the equipment, how to collect the data, how to plot the graph, and what question they are supposed to answer. Everything is mentioned in the lab book, and even students doing this kind of lab, their brain are not engaged in the process, and there is little or no reason to think about the physics content involved. That's why taking the lab course do not enhance student content knowledge. Uh, they, but for students who are doing this undergraduate research experience, they design, build, and carried out their own experiment, uh, and uh, opportunity to make decision and take time to look at it on this uh, URE's uh, type of lab. It adds value uh, on them. So the issue raised above reveals a fundamental constraint on the ability of the lab to support the learning of content in an associated lecture course. We now know the problem is students, they don't have to think, they just follow the procedure mentioned in the lab book. uh, then when they are done with the lab and when they left the lab room, they don't know what they did. And it is likely that students did learn the physics content associated with their experiment either in the project lab or URE, but the physics content formed only a narrow slice of typical lecture course. We'll be talking about it in the other slides. Uh, and also, we can use the lab course to enhance student content knowledge, but it requires more uh, overhead and more time than other methods. So far, from the Carlman and his collaborators' investigation, they found that uh, the traditional lab course they are structured, or they are more like a cookbook. That's why they are not very useful. Uh, then physics is an inherently of experimental science, and there is an increasing our awareness of the importance of the laboratory experience in physics educations. uh, association American Association of Physics Teacher, AAPT, they recommended the six focus area that should be in the undergraduate physics lab curriculum. They are constructing knowledge, modeling, designing experiment, developing technical and practical skills, analyzing and visualizing data, and communicating physics. Uh, so, in summary, in this the diagram, you can see the constructing knowledge. It overlap all other focus area. And what they are constructing knowledge, students collect, analyze, and interpret real data from personal observation of the physical world to develop the physical world view. Modeling, develop abstract representation of real systems studied in laboratory, understand their limitations and uncertainty, and make prediction using models. And other focus area, designing experiment, developing technical and practical laboratory skills, analyzing and visualizing data, and communicating science. Uh, I think they are all explain what they are. And the learning outcomes based on those focus area are they mention are to think like physicists and perform experimental investigation at an appropriate level for graduate schools, research lab, job in industry, public or private sector STEM careers. This is the learning outcomes they mention. Second one is prepare future teachers, uh, and third one is introduce non-physics measure to experimental investigation from a physics perspective, which will broaden their appreciation for the interdisciplinary nature of science and strengthen their readiness to participate in highly technical 21st century skill sets. In summary, this AAPT guideline is talking about shifting educational goal towards teaching experimentation rather than reinforcing content from the lecture class. Then the Carl Newman and Douglas Bond and their collaborators from University of British Columbia, they develop a new type of lab course to overcome this existing problem. Uh, uh, they that lab involves abandoning the goal of teaching content and instead aiming to teach important aspect of physics thinking for which lab are uniquely effective. The aspect relates to the process of scientific experimentation, such as formulating hypotheses and testing them by collecting data, figuring out how to improve the quality of data, using data to evaluate the validity of models, and deciding on suitable criteria for evaluations. They name this type of lab as a structured quantitative inquiry lab, SQI lab, it pronounced ski lab. uh, Basically they implement the idea from the here this undergraduate research experience where student valued the decision making and time to look or iterate their im- iterate their experiment, and those concept is or those finding was implemented when developing this skill lab. So here is a sample skill lab. They design it is pendulum for pros, uh, and this is the lab manual they have. Basically, here they mention about the tools they are supposed to use for this particular lab, the learning outcomes, and they give a little hint what they are supposed to do. That's all they mention in the lab manual instead of giving which button to push to collect the data. And here is the student group findings. So let me first talk what they are supposed to do here. Actually, they are supposed to evaluate that uh, time period of a simple pendulum depends on the angle of swing or not. And here, in the first round of the experiment, student found that this time period is does not depend on the angle. Uh, the second round, they repeat this experiment for several trials and reduce the uncertainty, and they can see the some dependence. And third round, here they collect the data for the 0 to 30 degree angle and able to figure it out that this period of a simple pendulum, uh, it depends on the angle for higher for larger angle, and they able to find out the second order quadratic deviation from small angle approximation. And here are the two comments from student uh, after this lab. First one is, in physics there is lots of simplification and approximation and things that we can ignore. When we do the experiment ourselves, we can see why physicists would do that. This is a really nice comment after doing this skill lab. Uh, Second one, the pendulum experiment we did at the beginning of the year. I think that really made a mark on me because I went in there expecting it or the period at 20 and 10 and 20 degrees to be the same because that's what I was taught in the class. And then when you finally figure out that, oh, it's supposed to be different, and then I was like, oh, I probably shouldn't be doing experiment with bias going on. uh, their research, like what this comment is referring is, in the class student were taught that a period of a pendulum is independent of the angle of swing, but they able to figure it out that is only true for a small angle approximation during this lab. And their research mentioned that uh, uh, for the lab which has already non answer like uh, finding the acceleration due to gravity, students know it is around 9.8 meter per second square. uh, uh, Students have less motivation to do that, and also even they do not have a good data from the lab, they try to manipulate the data to get the correct answer, and they try to remove those things on this skill lab. Here, Emily Smith, Natasha Holmes, and their collaborators, they evaluate the effectiveness of skill lab or lab similar lab that we call the experimentation. Here in this table, you can see that this first column is the standard lab we have, or the traditional lab. We have a they have 9 labs for the semester. Second one is experimentation, or the similar to ski lab. It has again a nine lab sessions, but the content they are going to cover here is less. They have a pendulum for 2 lab sessions. Why having the same lab for 2 lab sessions is important is student have a time to reflect their findings and work on iteration for improvement. And here pendulum lab, terminal velocity, Hooke's law, collision, and uh, project lab. So they are covering less content in comparison to our standard or the traditional cookbook lab. And their finding here is uh, the one is student engagement in experimentation. They found that students spend more time doing the lab. Uh, their their standard lab time was 115 minutes, and for the traditional lab, students spend about 91 minutes in average. But for this experimentation lab, they spend about 118 minutes in average. So they spend more time, or the engagement is enhanced. The second one is experimentation behavior. Students try to iterate their experiment in this experimentation type of lab. Second thing they examined was exam performance and found no measurable difference, very similar to the Carl Women and Natasha Holmes' previous finding. Uh, and the last thing they measured was attitude and belief about experimentation using the E-class and LES survey, and uh, they found that student attitude has changed towards the experimentation. So looks this experimentation or skill lab works well. And here is the second type of the lab developed, that's name is Investigative Science Learning Environment, ISLE, designed by Eugenia Itkina and co-workers from Rutgers University. In this type of the lab, students work in a group to develop explanations of new and surprising phenomena, and then design experiment to test those explanations. I'm not going to talk in details about it. I think we already have a talk from using Atkina in our studies before. Uh, then now, last thing I wanna talk in today's talk is even uh, what we have implemented in our lab course. Our current lab course here at UNCC, they are more close to the traditional lab. We have a physics 1 and physics 2 laboratory courses here. Have 10 standard labs, one makeup session, and the final exam during the semester. Uh, and our lab course is standalone, and it is a 1 credit separate lab course. And I have about 2,500 students per year in the lab course. So uh, uh, let's talk in details what we have or what we have implemented in our both lab courses. Here, this is for the physics 1 lab course, and the first lab I designed is it is about visualizing data in a graphical form. Students learn to plot a graph in a standard graph paper. They learn which variable goes along x-axis and which goes along y-axis, how to calculate the slope. Then second thing, they learn the least square feet uh, and calculate this fitting parameters using this approach. And the last thing that they are supposed to learn is to plot those data in Excel sheet, and again calculate those fit parameters. So uh, in general, we provide them this paper shown in this right here, which has the several circles with different radii. The length of this each box is 1 centimeter, and the area is 1 centimeter square. Students are supposed to collect the radius and area information by counting the number of boxes inside this circle. Then they plot a graph, uh, area versus radius graph. Then they saw some trend there. Then they linearize it, plotting area versus radius square graph. And they fitted this graph using the ruler and find the slope. They do this, they minimize the residuals, or they do the best fit using the least square fit method. Then finally they plot those data in Excel sheet, and they compare all these three type of, or three method of graphing. So this is the one focus area AAPT guideline uh, mentioned as discussed before. Uh, Lab 2, it is talking about the accuracy, precision, and uncertainty measurement. Here students learn uh, to uh, to collect the data with the uncertainty, and when they do the calculations, how those uncertainty propagates. So here we provide them this wooden block. Students measure the length, width, and height of this block with the uncertainty. Uncertainty involves instrumental uncertainty and the uncertainty from the measurement, or the standard deviation, or we can say the random errors. They learn how those uncertainty add up, and finally they calculate the volume and density with and report their finding with the uncertainty in the second lab. Third lab is about scientific inquiry. It is very similar to uh, uh, what we have in the ski lab for from British Columbia, but uh, it is little different. I'll talk about it. On this lab, we provide student 5 sets of pendulum bulb. They are of same size but different masses. Students are supposed to find out what factor affect the period of simple pendulum. They do not require any previous knowledge to do this lab. They set up a hypothesis. They design a lab to test the hypothesis, and at the end, they analyze those data and come up with the single equations like time period is equal, that depends on the some constant times the square root of the length. And one thing I like to highlight here uh, is case qualitative graph of your production for the period versus mass below. So for most of our lab, uh, we implemented the POE method, that is the production, observation, and explain method. What does that mean is, before doing the lab, student do the production, and research shows that this POE method is useful in enhancing student learning. Similarly, for the physics 2 lab, we have the first lab, we designed the electrostatics. The students learn different way of charging the materials, and one interesting thing I like to mention here is, when we teach them to like charge repel or to unlike charge attract, this concept is more abstract, but when they transfer the same type of charge on the two hanging these foam ball, they are wrapped with the aluminum foil. uh, when they saw this repelling these bulbs, these foam balls, it helps them to visualize the this effect. And in this electrostatic lab, students are supposed to uh, just based on the mass of this fumble, length of the string, the separation angle, they are supposed to theoretically calculate the charge on his fumble, and also they use the sensor to measure it. Another thing we implemented in our lab course, for example, for the capacitor lab, we asked students to use the easily available everyday materials like the aluminum foil and paper. They are supposed to make their own capacitors in the lab. Uh, they connect the capacitor. They try to improve the capacitance of the capacitor in their design, and they connect the capacitors in series, parallel, and explore their properties instead of using the standard equipment from the Pasco or the Vernier. So uh, in general, here are the summary of the changes we have implemented in our lab courses. One is the POE method, product observe explain method in most of the lab. Uh, we try to design the lab course starting from fundamental principle and utilizing commonly accessible equipment. Next thing is the index card. In our lab course, after each lab session, students are supposed to write an index card. They write what they learn in the lab. It is more like a 1 minute paper. And the next side of the index card, students write down the feedback. So what was the most interesting thing for this lab, or what was the most confusing thing? And most of this traditional lab course do not have a final exam, but we do have here that counts 20% of the total grade. And research shows that having a final exam, this is a summative final exam, it forces learning, or it enhances student learning. And also students take this lab course seriously. They know we are going to have a final exam. And if students copy the data, they do not take to the lab seriously, they are not going to do the final exam well, and it helps to spread the student grade for this course. uh, Furthermore, previously we have a 3 student working in one lab table, and we have a 36 student in lab room. That makes the lab so crowded. And from this semester, we reduced the student number to 2. Uh, uh, and the previous problem was when we have a 3 students, one student have nothing to do, and that person just keep talking and distracting even the other people, other groups. And hopefully that will overcome this issue. And last thing I like to say here is we have developed the fundamental of physics teaching course. It is 1 credit course to train the teaching assistant uh, to improve the students lab learning. And here is the future plan we are working on. uh, we are uh, planning to switch our all traditional lab courses to open-ended, less structured lab course. uh, our like we'll keep the graphing uncertainty lab as it is, but during the semester the instruction will fade away, and the our lab manual will be more like a one-page lab manual. What does that one-page lab manual means? The lab manual will have a title, the equipment, the tools they need, and the learning outcomes, and some hints only. So students are supposed to uh, design the equipment, the test it, and also learn to improve the precision of the data they are taking in the lab. Uh, we are furthermore we are like currently we have the worksheet. We are trying to eliminate the worksheet and ask students to write a lab report. And for the lab report, they will be using some programming language like Python, MATLAB for the analysis and data visualization. Uh, Also, one thing I forgot to mention on this slide is these days The AI tools is like we listen a lot about the AI and like a chat GPT, and we started in our lab course that students can use the AI, but they need to submit whatever they got and what they made a changes uh, in the report. uh, I think that's all I want to cover on this talk. And here are the selected references. I would like to acknowledge my current and previous institution where I worked before, and ANPA Division of Innovative Teaching, Scholarship of Teaching and Learning, and Physics Education, uh, and especially Dr. Rudra Kapli sir for helping me to go through uh, to go through all the materials and help me to learn. Thank you.
Thank you so much, Dr. Silwal, for great presentation. Now the floor is open for questions. So uh, please unmute and ask questions if you have any to Dr. Silwal, or you can type the questions in the chat box. I can read the questions. Okay, thank you so much.
Rudra sir, I'd like to ask one question to Mr.
Yes, please,
Mr. Am
please,
I
please go
audible?
ahead. Yep,
Yeah, okay,
please.
thank you, sir. When I just or when I help my students to perform experiment in oscillation, sir. So basically, we take 10 oscillations so as to minimize the error. And then, sir, am I clear in my voices? Hello.
Yes, yes.
Yes, sir. So on taking the period, so I asked them to go for 10 oscillations and ultimately divide it by 10 so as to get the period. So when I take the time duration for 10 oscillations, I usually take in 2 dp because in stopwatch there are 2 dps. However, while I'm writing, I'm just confused. Suppose, for an example, if the time period or if the time duration is 4.98 seconds, and then if I check the period, it will be divided by 10, so it will be around 0.498 seconds. Am I eligible to write 0.498 seconds? Does it violate the SF rule or not, sir?
I assume yes. You can write the 0.498 second because the 10 is a number and it doesn't have a uncertain, right? So I hope that should be okay.
However, I think we will have or the human is prone to only one SF, I think, after one DP, I think, right, sir? So suppose if it is 0.498, then we are certain only up to one DP. I think we are not certain up to other two DPs, additional two DPs. So does it make or are we correct in writing 0.498, or simply can we just round it up and can write 0.5 second?
Uh, 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 there is a rule about we say it is a significant figure, and uh, this why I assume 0.498 is correct is even we divide it by 10, 10 doesn't have it is same as 10.0. It is a number and it doesn't have a like, that's why it has a we can assume it has a three significant figure, and uh, with the number 0.498 it has a three significant figure. So I think both approaches should be fine.
Okay. So, however, our human reaction time, I think, it should not be greater than 1 dp, right, sir?
uh Let me go to the
Our human
uh,
reaction time, I think we are not greater than 1 dp in second, 1 decimal point in second. So I'm just confused. So just like if